Okay, so you should be with your nerve packet that we received last time that we met for class. And within the nerve packet, there's a couple different sections that we're going to be talking about or talking through. So we're going to talk a little bit about the design of a nerve cell, and then we're going to talk how that pertains to the spinal cord as well as the brain itself. So when we look at nerve cells, and most of the time when we talk about nerves, or when we talk about cells, excuse me, we talk about the fact that it's this nice round shape, and that's kind of where our brain goes to. We need to make a little bit of a transition when we talk about the nerves and what that cell is designed like, because a nerve cell has a much different function than a typical body cell. A typical body cell is set up so that all parts of the cell can be served very quickly. And so the nucleus is put at the core for protective measures, but it's also going to be the location where the nucleus could be and be equidistant from all locations or the furthest location of the cell membrane. And in the placement of that nucleus, we can ensure that no matter where an organelle is or no matter where a function has to happen within the cell, that nucleus is going to be centrally located, and therefore it will be very easy for it to take care of whatever it needs to in the most efficient manner. A nerve cell is not designed for really taking care of the cell contents or for producing or manufacturing products like your other body cells. The nerve cell is designed for speed. It is trying to carry these electrical impulses from one location of your body to another in the shortest time frame possible. And so in order to do that, they go away from that nice round circle shape that we think of our typical body cells having, and now it's going to become a very long, narrow, spindly shaped cell. So when you think of a nerve cell, the one end where the nucleus is going to be located is going to have kind of this starburst appearance with these little extensions coming off of the end of the nerve. And there's going to be a very long, narrow portion of the nerve. And at the opposite end, it's going to kind of fray again, little extensions that allow it to connect or meet up with an adjoining nerve cell. And so looking a lot more for length with the nerve than we are for that nice round shape. The nerve cell allowing for that speed is going to really be what causes your nervous system to be able to react and respond to things as quickly as it does. If you guys were to stand at the end of a football field and try to sprint to the other end zone, think about how long that would take you. So you're standing in one end zone, take off on a dead run as quickly as you can to get to the other end. You guys know that's going to take you some time to get from one location to another. Your nervous system is able to send electrical impulses so quickly that it could travel the length of a football field in less than a second. So from end zone to end zone in less than a second is how quickly it can send information to any part of your body. So when you condense that down and think about the fact that you are nowhere near the length of a football field, if your nervous system can travel that distance in less than a second, it kind of starts to make sense how you can get information and react to things in the short amount of time that you do. Because if it can span that distance, obviously your 5 or 6 foot frame is going to be very easy for it to send information to. Most people have had a situation where kind of something has happened and gone on around you and you react to it and you don't fully process what happened until after the situation is over, just because of how quickly your nervous system is able to allow you to react or respond to what's going on, even before you're fully aware of the entire situation. When we talk about the nervous system is going to really have two different parts. We have the central nervous system and we have the peripheral nervous system. So if you're looking at that first slide, it talks about the CNS and the PNS. So the CNS is going to be the abbreviation for the central nervous system. The PNS is going to be the abbreviation for the peripheral nervous system. And the difference between the two is that the central nervous system is going to be made up of your brain and your spinal cord. The peripheral nervous system is going to be all of the nerves that branch off of that. So you have nerves that branch off the bottom of your brain and they go out through holes in your skull and they serve your face, your tongue, your neck, the muscles in and around your neck and shoulders. And so Those nerves that come off of your brain would be considered to be peripheral nerves. Likewise, you have nerves that branch off of your spinal cord, and they are going to go out down your arms, all the way down to your fingertips. They go down your legs, all the way down to your toes. And those, again, nerves that travel off of that central piece of the spinal cord and go out to serve all the parts of your body are what we call peripheral nerves. So those are the two divisions of the two parts that we have within the nervous system. Now, a couple of things. With the nerves or the neurons that you guys have in the central nervous system, you are born with a number that you are going to have. And once those cells die, they are not coming back. So they don't go through the process of mitosis. They do not replicate themselves. You have the number that you are going to have for your lifetime, the day that you are born. Now, that number is a massive number. And if you live a normal life and don't expose yourself to a lot of toxic material or things of that nature, you will have the number of nerves in your central nervous system to last you your full lifetime. With the PNS is a little bit different. Not that these nerve cells are able to replicate, but they have a little bit more of an ability to repair and recover when they become damaged. And so the peripheral nervous system can repair damage if it's not too extensive. And on a good day, the repair process to your peripheral nervous system is going to be about 1 millimeter worth of repair. So if you have damage that covers a length of the nerve or a good portion of the nerve, and like I said, that's under the best of conditions, it would be able to repair 1 millimeter of the length of the nerve. And you have some nerves in your body. The longest nerve in your body is the sciatic nerve, which runs down the back of the leg from your hip down your leg, can be 3 feet long. So if you're talking about a repair process that is only happening at 1 millimeter a day, you can see why rehab and things like that can be months in duration. And again, keeping in mind that that's the best case scenario. If other things are going on with the body and that person is struggling in other areas, they might not be getting or maxing out that repair of 1 millimeter a day. So it could take potentially longer for their repair process. So looking at the spinal cord itself, the spinal cord is going to be the extension that comes out of the brain and runs down the vertebral column. So you have those vertebrae, those bones that are going to protect the spinal cord, because the consistency of the spinal cord is not overly durable. It's about the consistency of cooked spaghetti. And at most places in your spinal cord, it's going to be about the width of your pinky finger. There's a couple places throughout the spinal cord where it gets a little bit larger, but for the most part, if you look at your pinky finger, that's going to be the size of your spinal cord. So the two pictures that you have there on that particular slide shows you where the foramen magnum is. That's the hole in the skull where the spinal cord is actually going to exit. And then as you run down the spinal cord, you'll notice that there's a couple of enlargements there. You have the cervical enlargement and you have the lumbar enlargement. So those are both places where the spinal cord is going to be a little bit thicker than that pinky-sized reference that I just gave you. And if you think about what would be in those two locations, that's going to be the cervical enlargement is going to be roughly around the area where your arms are going to extend and be placed on your body. And so you have more nerves that are going to then have to go out to take care of your arms. So a little bit larger there because of that extra nerve supply that you need to go down to your arms. And likewise with the lumbar enlargement, we have that same case. These are going to be the nerves that are going to run down your legs and serve all the way down your legs to your toes. So a little bit more of a size increase there to make sure that you have enough nerves to take care of those body parts. The other thing that you have identified on that first list that I want to talk about is the cauda equina. So if you were to translate that, it means horse's tail. And if you look at where you are in the arrangement of the vertebrae, this would be in the lumbar vertebrae. And by the time you get down to those lumbars, your spinal cord is no longer intact, so to speak. It starts to fray and turn into these individual bundles. And because of how that spinal cord frays, they thought it looked like a horse's tail, and hence the name cauda equina for that end of your spinal cord. The second picture that you have to the far right is a little bit different because at this point they have removed all bone protection and you are looking at just the spinal cord by itself. So nothing around it to take care of it. You've stripped it of its protective layer, and now you are looking at just the material that makes up the spinal cord. So you can see the brainstem. That's that transition point as we are going from brain down into the spinal cord. You can again see those two enlarged areas where you have extra nerves to take care of those additional body parts. And then the very last one that you have on this particular sheet talks about the filum terminale. And this is actually where the spinal cord is going to end. So as it continues to run down through those lumbar vertebrae, it will make its way down through the sacrum to the coccyx or the tailbone. And as it gets there, it continues to become more narrow, begins to taper down in size. And so the filum terminale is referencing the end, terminal, the end of the spinal cord. If you go to the next slide, it talks about the Meninge layers. And Meninge layers are both in the spinal cord as well as in your brain. So this encompasses the entire area, but we're going to talk about it here as it's associated with the spinal cord. So these are 3 layers of connective tissue that you guys have that are going to surround the spinal cord and offer protection to the spinal cord. So the 3 layers that you have the dura mater, the arachnoid mater, and the pia mater. So the dura mater is, as I mentioned on the slide, also referred to as tough mother. It is a very thick, durable sheet of connective tissue that is going to lay over or be on the outside of this entire setup. So it is the outermost layer that you guys have. And because it's that outermost layer, it really doesn't take shape. It doesn't adhere or form to the brain or the spinal cord. And so it's just like a blanket that kind of lays over everything. Then you have the arachnoid mater. And the arachnoid mater, most people when they hear arachnoid do make that association to spider. And the reason that we call this the spider layer is because if you were to look at just this sheet of connective tissue, there are a lot of holes and openings in it. It's not a solid sheet. And that is to allow the cerebral spinal fluid that is also located in this area to be able to freely flow in between the meninge layers. If it was a broad sheet, it would kind of cut off that circulation. So by having the holes and the gaps in the arachnoid mater, it can get to the dura mater, the arachnoid mater, and the pia mater and flow easily between those 3 layers. Now, the cerebral spinal fluid is a material that is found in and around the central nervous system. And basically, it's like bath water. The cerebral spinal fluid is going to bathe over the brain and the spinal cord. It's going to bring nutrients to these 2 body parts. It's going to make sure that the ion concentrations are where they need to be. It also helps to protect, kind of create this liquid environment that your brain and your spinal cord exist in so that they don't get bounced around and become damaged. So you guys might, for whatever reason, you're in a car accident or something like that, and you kind of get slammed around a little bit, that cerebral spinal fluid is going to help buffer that so that you don't do damage to the brain. Because of the close proximity of the brain to the surrounding bone, if it starts to slam around within your skull, you can bruise the brain very easily. And as those blood vessels get broken, you have that bleeding. There's not a lot of extra room. So if there's too much bleeding, it starts to create pressure and compress the brain, and then it can't function the way that it's supposed to. The last layer is the pia mater. Now, this is the innermost layer. So it is going to adhere to the brain and the spinal cord perfectly. It's like a layer of saran wrap that just is very tightly coated over those 2 body parts and would follow any crevices, peaks, valleys, any formations. The pia mater would follow that to a T. So if you look at the next slide, it talks a little bit more about the cerebral spinal fluid. And the cerebral spinal fluid, as I mentioned earlier, is kind of like bath water. And you guys know with bath water, that's not something you want to share. When somebody in your household gets done taking a bath, you're going to drain out that bath water and bring in clean if anybody else needs to bathe. And you have that same sort of setup within the brain and the spinal cord. These are 2 of the most important parts that we have in the human body. And so you want to make sure that it is living in a clean, healthy environment. So there's actually a faucet that will, so to speak, that will bring more cerebral spinal fluid in to this area There's also a drain that will take out the old. So if you look at your information there, it talks about the choroid plexus. This is going to be the structure that would act like a faucet, pumping in new cerebral spinal fluid. And then you have what are called the arachnoid villi. That's about halfway down in that informational set. The arachnoid villi are like tiny little straws, and they work like the drain. They will actually suck and pull out that cerebral spinal fluid after it has been circulating for a while to make sure that if it's picked up any debris or foreign bodies or anything like that, that instead of continuing to circulate them around these cerebral or around the brain and the spinal cord, that we're draining that off and getting rid of it and letting your immune system deal with it at that point. It talks about the volume only being 120 milliliters, and typically I will have my classes measure this out so that they can see it. To say 120 mils, um, doesn't really do much in the visual perception. If you think about a 12-ounce can of pop, that's about 350 milliliters. So if you can kind of break that down in your head as to what that would look like, then about a third of that a can of soda would be all the cerebral spinal fluid that you have within your brain and your spinal cord. So we are not talking about a lot of material because there's not a lot of room for it to be. You just need enough to bathe over those two body parts and help take care of them. As I mentioned, has the job of bringing in nutrients, making sure that the ions that are needed for the brain to work and the spinal cord to work properly are in the right concentrations and consistently being brought in so that the brain can do what it needs to do. The next slide that you guys have, just a little bit of a visual showing you the dura, the arachnoid, and the pia mater and their location. As I mentioned before, dura mater is the outermost layer. Arachnoid would be in the middle. The only thing that I don't really care for in this picture is that it shows the arachnoid mater as being solid, and you don't really get that visual of it being more of a web or net-like structure. And then you can see how the pia mater follows to the rises and falls of the spinal cord, as I mentioned earlier. The next slide that we have talks about the parts of the spinal cord. And I'm going to go through these. First of all, we have two types of matter that make up the brain and the spinal cord, white matter and gray matter. Now, white matter is going to be the bundles of nerves that you guys have that do not contain the white matter is going to be the material that does contain a protective covering that you have over the surface of the nerves. Gray matter lacks that protective covering. And if you watch medical shows and things like that, they will talk about they can see gray matter or they can see white matter. Depending on what structure you are in, the brain or the spinal cord, that will tell you the level of severity of the injury. When you look at the picture of the spinal cord, you will notice that the white matter is the outer portion of the spinal cord and the gray matter is at the core. This is just the reverse in the brain. In the brain, gray matter is on the outside, the white matter is on the inside. So if you can see gray matter in the spinal cord, you know that you have a deeper injury. If you can see gray matter in the brain, you are at a surface injury. Not that either one of them is great, but like I said, because of the location of white and gray matter being in different spots within the brain and the spinal cord, it can tell you a little bit about everything that's involved with the injury itself. So white matter has a protective covering over the nerve cell. Gray matter lacks that protective covering. Now, one of the biggest things that indicates is that because of the protective covering, your white matter works faster than gray matter. That protective covering lets those nerve cells carry impulses at a faster rate compared to gray matter. Both of them are still very fast in their ability to carry nerve impulses, but that protective coating over those nerve cells lets it go just a little bit quicker than the gray matter. For the white matter, I'm going to stay there for just a second. And on there you have a lateral funiculus that is identified. You have an anterior funiculus and a posterior funiculus. So if you take just a second to find those, the lateral, the anterior, and the posterior funiculus. Lateral is about halfway down on the left. Anterior is the last one on the right column, and posterior is the first one in the right column. So a funiculus is a really big name, and all it means is you have a large collection or a bundle of white matter. And if you look at where those arrows are pointing to, Those are 3 places within the spinal cord where you have very large masses or groups of white matter. On the other side, if you look at the horns, you have an anterior horn, excuse me, you have a posterior horn, and then you have I don't have it on here, or I'm missing it right now. But you do have horns also that are going to refer to the bundles of gray matter. And anytime that you see horn as it pertains to the spinal cord, that's telling you that you have a large collection of those gray cells all bundled or in one spot. Now, some of the other terms that you guys have on here, you have the anterior median fissure, and then you also have the posterior median sulcus. So anterior median fissure is bottom right side, and the posterior median sulcus is going to be second one down on the right. Now, you look at those and it looks like there's just 2 lines that are cutting into the spinal cord. Those are actually places where the spinal cord is separated. So if you were to be able to see an actual spinal cord, those are 2 divisions and cuts basically that you have within the spinal cord tissue itself. So if you look just below the posterior median sulcus, you have the gray commissure that is identified. The gray commissure is the only place within the spinal cord where it is completely attached from the right side to the left side. Because of that posterior sulcus and the anterior median fissure, those are cuts that divide the spinal cord. So it's only at that gray commissure where you have a true connection, which is a very small sliver of tissue that's actually holding and allowing the right and the left side of your spinal cord to be able to communicate with each other. Then if you look at the very center of that, you have the central canal. That is a tiny little opening that you have at the core of your spinal cord, and cerebral spinal fluid is going to circulate through that tiny little opening. So still flushing that CSF through the spinal cord as well as on the outside of the surface of the spinal cord. So I know probably some new terms for some of you as you guys are looking at the spinal cord, but if you break them down, usually not too bad. They're just indicating those areas where you have large masses of either white matter or large masses of gray matter, and then showing you the 2 cuts or the 2 divisions that you have in the spinal cord, creating a right side of the spinal cord and a left side of the spinal cord. The last things that we have on there that we haven't talked about are the spinal nerves. And so you have a dorsal root ganglion, and then it also identifies the spinal nerve on the right-hand side. So as mentioned before, you have your vertebrae, which are going to surround the spinal cord itself to help protect it. But the information that's traveling up and down your spinal cord has to be able to get out to all the parts of your body. So if you look at those 2 nerves that they're showing you, you can see how they branch and break off of the spinal cord. And as they move away from the spinal cord, they start to get a little bit bigger in size. And even though it shows them here like they end, those nerves would continue to extend outward, and they would run down to whatever part of the body they need to take care of. They might run down your shoulder, down to your elbow. They might run down your leg, down to your toes. But those nerves are going to branch off of that spinal cord and then go out to whatever part of the body they need to take care of. So the next part of the packet talks about your reflex circuit. And you basically have 3 parts to your reflex circuit. You have a part that's going to bring the information in, you have a part that's going to process the information, and then you have a part that is going to carry out how you're going to respond to the information that came in. So your sensory information is going to be picked up by receptors. You guys have receptors head to toe throughout your body that are going to pick up on temperature differences, are going to pick up on different smells that are in the air, things like that. So any sensory information that is around your body, you have a receptor somewhere that is going to pick up on that. Once that receptor picks up on that sensory information, it's going to send it to your central nervous system. And there, the brain or the spinal cord is going to process that and figure out how you want to respond to it. So you're driving down the road and you come up on a stoplight and it's green and all of a sudden it goes to yellow. Your receptors see that color change, they send that information to your brain. Now your brain has to process it. Are we going to stop for the yellow light, or are we going to accelerate through the yellow light? Once your brain figures out what your response is going to be, it's going to send that information to your effectors, your muscles, or your endocrine glands, depending on if the response is going to be a change within the body or a physical response that you need to carry out. So for some people, they would decide that they are going to pick up their foot, put it on the brake, and stop for the yellow light. Other people would pick up their foot or push their foot further on the accelerator and go through the yellow light. But that is your effector actually carrying out whatever response your brain came up with. Now, the thing with the reflex circuit is people will respond differently based on their past experiences. And this is key when you're dealing with people to remember. You will have some people that are very pleasant, they're great to be around because in their past experiences, they've had great experiences. They've been surrounded by great people. And you will have other people that when you have to deal with them, they are very grumpy. They are not very agreeable. And that is because in their past experiences, they haven't had great experiences. And so now they're drawing on those past experiences to determine how this one in the present is going to turn out. So just kind of keep that in mind when you are dealing with patients or people that are not that agreeable. They're only pulling from their past experiences and what they've been exposed to decide or determine within their central nervous system how they're going to respond to this one at hand. Like the stoplight example, if you've been given 5 tickets for going through a red light, you're probably going to respond by slowing down and braking. If you've never received a ticket, you might be willing to push your luck and accelerate through the yellow light. So you make the decisions in the here and now based on those past experiences. The next one talks about the parts of a spinal reflex, shows you here how the information comes in from a receptor. You can see that red line at number 1, and it travels into the nerve. So the nerve takes it to the spinal cord. That information is then delivered to the spinal cord. Spinal cord is going to figure out how you want to respond to that, and then it just shoots it out a different nerve, and that is going to link up to an effector. In this case, it's a muscle, and that muscle will contract and move how you need it to in order to carry out whatever response you need. So if you are stepping on a sharp tack, receptors are going to feel that pain. They're going to send that pain through the red line to your spinal cord. And in the red line, I know yours is, sorry, gray and black and white. So 1 and 2 are the red lines coming into the spinal cord. And then at right about 3, it changes to a different nerve set. And now we're going to process that information and we're going to kick out number 4, a response to that muscle to tell you to contract the muscle and pick your foot up off of that tack so you don't continue to drive your foot further down on it and push it farther into your foot. So that's just a very simple way that you can have a reflex and respond to a situation. You'll notice this one doesn't go all the way to the brain. This is a basic enough response that you can deal with it at the spinal cord level, and you don't have to take the time for it to travel all the way up to the brain, because while that impulse, that sensory information is traveling, the further it has to travel, the more you're putting your foot down on that tack. So if it's a very basic response that you're trying to come up with, sometimes the spinal cord is able to process it and save you that extra time of having to send the information all the way up to the brain, letting your brain figure out what to do with it, and then sending it all the way back down to the muscle. The next one that you have talks about the ascending and descending tracks. And we do not need to spend time. I know it gives you the name of the ascending and the descending tracks. We do not need to memorize those for our purposes. But what you need to understand is that you have bundles or tracks within your spinal cord that are very much like elevators, and they take information one direction and one direction only. And so this is so that you don't get a situation where you're sending sensory information up to the brain and your brain is trying to send information back down to a body part. So if information was able to run on the same tracks, then, like I said, you would have situations where information was trying to come in, information was trying to get out, and they would block each other and it wouldn't go anywhere. So obviously not a good situation. So within the spinal cord, you have very specific locations that will only take information up to the brain. When the brain has processed it and figured out how you're going to respond to it, then you are going to send that information back down in a different set of tracks and avoid that traffic jam. Ascending tracks are going to be the tracks that are going to bring information up to the brain, and anything that is in an ascending track is sensory information. The descending tracks are responsible for sending information back down. And so this is going to be your effector or your motor response, what your body is actually going to physically do in order to respond to what's going on around your body. The peripheral nerves that we have, it talks about the two types, the cranial nerves and the spinal nerves. And I kind of touched on this already on the first slide. Cranial nerves are going to be those nerves that come directly out of the brain, and spinal nerves are going to be those that come out of the spinal cord. So we're going to talk specifically about the cranial nerves and do a little bit with those in our last meeting that we have together, as well as do some things with the spinal nerves as well. So you guys will have a chance to work with both of those nerve sets a little bit when we meet for our final class. But just knowing they're named for where they come out of. If they come out of their brain, they're cranial. If they come out of the spinal cord, they're spinal. And then the last slide that I want you guys to jump to is the one that has the spinal nerves and just shows you. The only thing that I dislike about this picture is, again, it shows the nerves as being cut. The nerves that are coming out of the shoulder would go all the way down the arm. The nerves that are coming out of the hip would go all the way down the leg. They do not stop like that. They continue, they extend on. They are very long nerves in nature. They just don't depict that here in this particular image. So it shows you the different cranial nerves, thoracic nerves, lumbar nerves, sacral, and coccygeal nerves that you guys have. So they branch off of the spinal cord, they extend out to the parts of the body, and just like your vertebrae get a number, you also have your cervical nerves to go with that. The only difference is if you look for the cervical nerves, there was only 7 cervical bones, but you are identified with 8 cervical nerves. And the reason for that is you have a nerve that comes out of the top as well as the bottom of C1. So that first cervical vertebrae, there is a nerve that branches out of the very top of it, and then there's one that comes out of the bottom as well. For all the other vertebrae, the nerve would branch out of the bottom side, so they only get one out of those. And that's why you see an extra cervical nerve compared to how many cervical bones we have within the stack. So just if you are more of a visual learner, this slide is kind of for you so that you can see how those nerves are coming off of that spinal cord and then how they would extend down to serve and outreach to all the parts of the body. So that takes us to our brain information. So I'm going to stop there because that's going to be our last talk that we have. The next time that we meet for our face-to-face meeting, I need you guys to bring everything that you have as far as your muscle notes. We've had a couple videos over muscles. Those are going to be put to use the next time that we have class. So please make sure anything that you have in regard to that, you bring that with you and have that ready to go. If you have any questions between now and then, give me an email and I will talk to you later.